Let us now study characteristics and applications of self-excited DC generators. In our last video, we have seen that there are three types of generator characteristics: open circuit characteristic, internal or total characteristic, and external characteristic. Let us first of all see the open circuit characteristic of self-excited generators. Now to plot the OCC of self-excited generators, the field winding of self-excited generators, that is shunt or series generator, is first of all disconnected and it is connected to separate independent DC power supply. Then the generator is operated at no load and it is driven with the help of a prime mover, and the speed of prime mover is maintained constant, which is equal to the rated speed of machine. Now the exciting current or field current flowing through the field winding IF, it can be varied with the help of this potentiometer. Now the current flowing through the field winding IF, it can be read with the help of this ammeter, which is connected in series with the field winding. Now the terminal voltage of generator at no load, which is nothing but the generated EMF EG, it can be noted for various values of field currents IF. So this field current IF is increased in steps, and for each IF corresponding value of generated EMF is noted. Now with the help of these readings, we can plot the open circuit characteristic. So this open circuit characteristic, it is the curve between generated EMF EG and field current IF. The shape of open circuit characteristic of self-excited generator, it is similar to that of separately excited generator. So as studied earlier, when the field current IF is equal to 0, induced EMF is equal to OA, which is not equal to 0. This EMF is because of the residual magnetic flux. Now, during this portion AB, the reluctance of iron path is very small, and therefore as reluctance of air is constant, the relationship is linear. That means with increase in IF, there is increase in flux, and therefore there is increase in the generated EMF EG. But after point B, we have to consider the reluctance of iron path also, because it is not negligible now and therefore the curve bends, and after point C the poles get saturated and the generated EMF EG remains almost constant even if the field current IF is increased. Let us now see internal and external characteristics of DC shunt generator. In case of DC shunt generator, you know that the field winding, that is F1, F2, it is connected in parallel with armature, that is A1, A2. Now to draw the external characteristic of this DC shunt generator, the generator is driven at constant speed with the help of prime mover. The speed is maintained at the rated speed of machine. The current flowing through this field winding, that is IF, it is also maintained constant with the help of this variable resistance R, which is connected in series with the field winding. So with the help of this R, we can control the current in the field winding, and the current in field winding is also maintained constant. Then the load is gradually increased from no load to full load. And for each load current IL, corresponding value of the terminal voltage V is noted. And from the readings of terminal voltage V and load current IL, we can plot the external characteristic, which is the characteristic between terminal voltage V and load current IL. So it can be observed from this external characteristic that as the load current is increased, the terminal voltage decreases. So with increase in load, there is decrease in terminal voltage. Now the reduction in terminal voltage with increase in load is because of three main reasons. The first reason is the armature resistance drop IARA. So as the load increases, armature current also increases. And with increase in armature current, armature resistance drop IARA increases. And because of increase in IARA, terminal voltage V decreases. Now the second reason is the effect of armature reaction. So as we increase the load, armature current increases, and therefore demagnetization effect of armature reaction also increases. So because of this demagnetization effect, the magnetic flux becomes weak and it reduces the generated EMF EG, and therefore terminal voltage V also reduces. And the third reason of reduction of V is, in this case, the field current IF, it depends on V. So if there is reduction in terminal voltage V, there is reduction in field current. And if field current is not maintained constant, then with reduction in field current, there is reduction in flux, and due to that, there is reduction in EG and terminal voltage V. And therefore, the external characteristic of shunt generator is drooping. Means as load current is increased, terminal voltage decreases. And this droop in case of DC shunt generator is more as compared to the separately excited generator, because in case of separately excited generator, the field is excited by separate independent power supply, and therefore in that case field current IF is not dependent on terminal voltage V. Let us now see how the terminal voltage V varies for large values of load current IL. Now the portion AB of the characteristic, this portion AB, it is the working region of the generator. Means generator always works in portion AB and it is the stable region, and it never works in this unstable region BC. Now let us see what happens in portion AB. Now the current drawn by load, it is equal to voltage across load divided by resistance of load. So current drawn by load IL, it is equal to terminal voltage V divided by load resistance RL. Now if load resistance RL is reduced, current drawn by load IL should increase. So this happens in this region AB. So in region AB, with increase in load current IL, there is small drop in voltage V, and as load resistance is reduced, load current increases. So this point B, it is called as breakdown point. Now at this breakdown point, the current supplied by the generator is many times greater than its normal current, and therefore there is excessive IARA voltage drop in armature, as well as there is excessive voltage drop due to armature reaction. And because of excessive IARA drop and because of excessive armature reaction drop, this terminal voltage V reduces drastically. And therefore, even if the load resistance is reduced, the load current decreases and it will not increase. Means it will not follow the Ohm's law, because this terminal voltage V, it is not constant. It drastically reduces for large values of armature current because of large IARA voltage drop and because of large armature reaction voltage drop. Now if this continues, then at point C, the terminal voltage reduces to 0, and this is equivalent to the short circuited generator. So at point C, actually the generator gets short circuited and the terminal voltage reduces to 0. Let us now see the internal or total characteristic of DC shunt generator. We have seen that internal characteristic is the curve between induced EMF E in armature and armature current IA. Now here armature current IA and load current IL are almost equal because the field current IF is very small as compared to the load current IL. Now to obtain the internal characteristic, we have to add IARA voltage drop into the external characteristic. So this curve 2, it shows the external characteristic. Now to this external characteristic, for each value of current, if voltage drop in armature IARA is added, we will get the curve 1. And this curve 1 is nothing but the internal or total characteristic of DC shunt generator. Now while drawing this internal characteristic, you have to remember that IA is the sum of the load current IL and the field current IF. The difference between external characteristic curve, that is curve 2, and internal characteristic curve, that is curve 1, it is always equal to the ohmic drop in armature, that is IA into RA. We will now see the internal and external characteristic of DC series generator. In case of series generator, the field winding S1, S2, it is connected in series with armature A1, A2. Now again, to plot the external characteristic, we have to drive the generator at constant speed, which is equal to the rated speed of machine. Then the load is gradually increased in steps. And for each value of load current IL, we can note the corresponding value of terminal voltage V. And then we can plot the terminal voltage V versus the load current IL, which is nothing but the external characteristic of DC series generator. In case of DC series generator, field winding and armature, these two are connected in series. So when load increases, armature current increases and the same current is flowing through the field winding. So with increase in load current, there is increase in armature current as well as increase in field current. So with increase in field current, there is increase in flux. And with increase in flux, there is increase in the generated EMF. And therefore, terminal voltage V also increases. So you can see from this external characteristic that as load current increases, terminal voltage also increases in case of DC series generator. But for higher values of load current, after saturation of filled poles, the flux will not increase and therefore generated EMF and hence V will also remain almost constant. So for low values of load current, as load current increases, terminal voltage V also increases. And after saturation, V remains almost constant. Means V will not increase much even if the load current IL is increased. Now, if we want to plot internal characteristic, then we have to add ohmic voltage drop in armature circuit, that is IARA, into the external characteristic. So if IARA drop is added to the curve 2, that is to the external characteristic, then we will get the internal characteristic. That is the characteristic between the induced EMF in armature E and the armature current IA. So this curve 1, it is the internal characteristic, and the external characteristic is always below the internal characteristic, and the difference between two, it is the ohmic drop in armature circuit, that is ohmic drop in armature as well as in series field winding and in the voltage drop in brushes. So if all these drops are subtracted from the internal characteristic, we will get the external characteristic. Let us now see the external characteristic of compound generator. Now, compound generator is a combination of shunt and series. We have seen that shunt generator has drooping characteristic, means its terminal voltage decreases with increase in load, whereas series generator has rising characteristic, means its terminal voltage increases with increase in load. So here you can see curve 1. So this curve 1 is one external characteristic in which series excitation is adjusted such that the terminal voltage at no load is equal to the terminal voltage at full load. So here you can see that the terminal voltage at no load and terminal voltage at full load, both the voltages are same. So in this case, the voltage remains practically constant from no load to full load. Such type of generator, it is called as level compounded or flat compounded generator. So this curve 1, it shows the external characteristic of level compounded generator. Now see the characteristic shown by curve 2. Now in this case, the voltage at full load is greater than the terminal voltage at no load. Means the terminal voltage increases with increase in load. So such type of compound generator is called as over compounded generator. So this curve 2, it shows external characteristic of over compounded generator in which the terminal voltage increases with increase in load. Now see the characteristic curve 3. Now in this case, with increase in load, there is reduction in terminal voltage V. Means as load current increases, terminal voltage decreases. So such type of compound generator, it is called as under compounded generator. So the characteristic curve shown by this curve 3, it is the external characteristic of under compounded generator. Now for all these three generators, that is over compounded, level compounded and under compounded, the flux produced by series field and shunt field, it is in the same direction. Means series field aids the shunt field. And that's why these three generators are called as cumulatively compounded generators. Now if the series field opposes the shunt field, means both series field and shunt field are in opposite direction, then the external characteristic will be highly drooping, and it is shown by this curve 4. So here you can see that this characteristic is highly drooping because the series field is opposite to that of shunt field, and therefore this type of generator, it is called as differentially compounded generator. So the external characteristic of differential compounded generator is the characteristic shown by this curve 4. Now we will see applications of DC generators. So actually at present DC generators are rarely used, and everywhere we use AC generators. But we will see the areas where these different types of DC generators can be utilized. So you know that in case of shunt generator, the characteristic is drooping and their terminal voltage decreases with increase in load. But the terminal voltage can be maintained constant with the help of the flux control, means by using automatic field regulators. So with automatic field current control, we can maintain the generated voltage constant. and therefore the shunt generators can be used for ordinary lighting and power supply purposes because of their constant voltage. Then shunt generators can also be used for charging batteries. Then it can be used as exciter to supply the field winding of AC generators. Means field winding of AC generator need DC excitation, and it can be provided by shunt generator. Now second type is series generator. Now in case of series generator, the characteristic is rising and therefore it cannot be used as power supply. But series generator, it can be used as voltage booster in distribution system. So when current flows through a feeder, there is voltage drop, and therefore receiving end voltage is always less than sending end voltage. The drop in feeder can be compensated by using a series generator because the characteristic of series generator is rising. So DC series generator, it can be used as voltage booster in distribution system. It can also be used in arc lamps for lighting. Let us now see applications of compound generator. The most widely used generator is the cumulatively compounded generator because the shape of the characteristic can be adjusted by adjusting series and shunt field ampere turns. Now the over compounded generator, it can be used for supplying power through a long feeder because when current flows through a feeder, voltage drop takes place, and this voltage drop can be compensated by the rising characteristic of over compounded generator, and therefore over compounded generator can be used to supply power through long feeder. If length of the feeder is short, then we can use flat compounded generator. Differentially compounded generators are used for arc welding because in differentially compounded generators, as current increases, voltage decreases, and therefore these generators are suitable for arc welding. Now finally, separately excited generators. Now these generators are expensive as compared to self-excited generators because DC separately excited generators, they need separate source of DC power for field excitation, and therefore separately excited generators are used only when the performance of self-excited generator is unsatisfactory for a particular application, or in an application where quick and more precise field control is required. In such cases only we can use separately excited generators. Thank you. Stay home, stay safe.